Hello everyone, so my name is Florian Felten and today I will present you our paper called Metaheuristics-based exploration strategies for multi-objective reinforcement learning. So this work was done with Grégoire Danois, Elga Zalitalbi and Pascal Bouvry. So we did this work at the University of Luxembourg and this work was supported by the Luxembourg National Research Fund. Let us start with defining the problem setting, so the thing that we want to tackle today. Well, with reinforcement learning, it is a technique which has been around for quite a few years, but recently it started to get even more hype because we realized that it was actually very efficient to play games, for example, Atari games, and even more recently, we applied this technique also to real-world problems, and for example, it was used to tackle a 50-year-old biology challenge, which is called the protein folding challenge. So it is very powerful and very promising for the future. How does it work? So in reinforcement learning, you have two components. So the first component is the environment. It is really the problem that you want to tackle. It contains possible states and you can realize actions to interact with the environment as to modify those states. And it will give you a feedback a posteriori, so after you perform the action, to know if the action was good or bad. The second component in reinforcement learning is the agent, and the agent's task is to perform actions to interact with the environment. Well, the agent's goal is to learn the best action that it can do for every state, and it does that using a reward signal. So how does it go? The agent perceives the current state of the environment and decides to undertake an action. After the action has been performed in the environment will give a reward to the agent to say if it was good or bad. In the agent, we have two subparts, which are the learning and the execution. So in the learning, our goal is really to estimate the quality of performing an action from a state. It is called a Q value and it is expressed by the equation that you see on the slide. So it doesn't only depend on the immediate reward, it also depends on the subsequent reward that you will get in the states after. So it is discounted, you can control the discount factor. And so once we have a good estimate for every state action, we can actually pass to the execution. So our goal here is for agent to use an optimal behavior. So we want to follow a policy which maximizes the expected discounted return. So we want to choose an action from every state. So from a state to choose an action, we just use the action which maximizes the Q values, so the estimates that we currently have. Yet, many problems involve multiple objectives. For example, if you want an agent which drives an autonomous car, well, it has to minimize its energy usage, and also you want to minimize the time to destinations. And those two objectives are actually conflicting because minimizing energy usage means actually going slower. So you will take more time to go to your destination. So what we need to do is to find the best trade-off as to represent the user's preference. And the same goes for satellite imagery or commuting. So we really have to deal with these trade-offs and find good balance between these objectives. In the literature, what we use are toy problems, and one of the well-known toy problem is called the deep sea treasure problem, where you control a submarine, and the submarine task is to find treasures under the sea. So as you can see, there is a map, and the submarine can perceive its XY coordinates, so it doesn't see the whole map. It can go into the 4 cardinal direction, and whenever it reaches a treasure, the game ends and we can retry, so we can start again from the beginning. So we have actually 2 objectives in here, which is the first, we want to maximize the treasure value, but also we want to minimize the number of moves. And as you can see, these are conflicting because you have to go far away to go to bigger treasure. So we need to find the good balance, so the good trade-offs into that. So here the difference with classical reinforcement learning is now we have rewards that become vectors. Well, currently the established way to solve multi-objectives problem is called multi-objectives optimization. And actually we have more than 50 years of background using these techniques. And so they rely on the concept of Pareto optimality. So the Pareto optimality, so we have solution points, which actually we can compare. So all of our solution points are characterized by vector evaluations. For example, my blue point here, I can compare it to my red point, and actually I know that my blue point is better than the red point. We say that it dominates the red point. Why? Because both objectives are better than the red points. However, because we have many components in the evaluation, so because it's a vector, sometimes we have points which are better in one objective but worse in another objective, so which means these points are actually incomparable, and which is why we need to return a set of solutions, because we don't know yet the true preferences of the user. So we return a set as to assess for the different trade-offs that we can make. However, up to now, most of the techniques require a complete and accurate model of the environment. So for example, in the DST, it would mean that you have the full layout of the map. And now we have, since a few years, multi-objective reinforcement learning, which deals with the vector rewards. And what it changes, as you can see, the rewards become vectors. So how do we deal with those vectorial rewards in multi-objective reinforcement learning? So the first way on the left of the slide is to transform the reward vector into scalar and to learn only one policy, just like using plain old standard reinforcement learning. The other way is actually the child between reinforcement learning and multi-objective optimization, because we learn multiple policies, so multiple optimal behaviors for the agent. We can do it with two ways. So the first one is inner loop MORL, which proposes to learn all at the same time. So we really deal with vectors and sets inside the learning algorithm. And the second one is outer loop, where we just apply different scalarization. So we transform the vectors into scalars, but with different ways, and we launch the training. So we train multiple times. We will interest ourselves into multi-policy, multi-objective reinforcement learning in this paper. So let's see how it looks like, so how it is used. So, well, it is used in a train test perspective. So what does it mean? So first we will have a training part and then a testing part. So it is not an online learning algorithm anymore, because we don't have the true user's preferences at the moment of the training. So we start from MOMDP, which means multi-objectives Markov decision process, which is our problem, and we apply the algorithm to that. And the output of our algorithm is the solution set, which accounts for all the optimal behaviors according to the trade-offs that you want to make. Once we have that, the user can make a choice. So it can choose the best solution that he wants, and the algorithm is able to retrieve and to perform the linked behavior. So for example, in the deep sea treasure, you have an example of the Pareto front. So those are all the optimal behaviors. And what does it mean? So it means all of the treasures with the shortest path to these treasures. So for example, in the selection phase, my user can choose first the blue point, and the submarine will go to the treasure 24. But after a while, the user maybe changes his preference, and he wants to go to 124. Well, the algorithm is able, by choosing the red point, the algorithm is able to retrieve the path to the treasure 124. And that is without the need to retrain, which is the big difference with classical reinforcement learning. So our goal here for the first phase is really to learn multiple policies, which leads to the various Pareto optimal point as to offer a wide variety of choices to the user. Well, let us see now the inner loop MORL, how it works, that we use in our paper. So we deal with rewards as a vector form, so the reward have M components because we have M objectives. Well, actually, our Q values, now they become Q sets. If you remember from multi-objective optimization, well, our solutions are sets. So for example, in the subset of the deep sea treasure that you can see here, my Q set for going left is 16 minus 1 because I have. Actually, if I go left, I have only 1 point because I finish my problem at this moment. So yeah, I finish if I go to the cell with 16, and it cost me 1 move. If I go to the right, however, you can see that I have various trade-offs. So I have various optimal solutions. I can go to 16 in 3 moves, or I can go to 50 in 4 moves. And same goes for down or up. So as you can see, those Q sets, they really represent the best, the optimal trade-offs that you can reach. So where to go? So in a normally with classical RL, what we do is that, for example, we use epsilon greedy to choose the move. So what it does is that with probability epsilon, we choose the action which has the best Q value at the moment, so the best estimate at the moment, and we take a random action otherwise. However, in this setting now we are dealing with sets which are not scalar values, so it doesn't work anymore. And remember, our goal still is to learn multiple optimal policies. So actually this is called the exploration-exploitation dilemma, and it's actually quite common situation in optimization. The intuition is that we have known good points, and we want to see if in the neighborhood of those points we cannot just make really small change and improve them. So this is called the exploitation, because we exploit what we know. On the other hand, we want also to explore like really far away from the points we know, because maybe there are good peaks like at the other end of the problem. Well, for the exploitation, it has already been tackled in various papers. So the idea is to find a function to quantify the quality of the Q set, so that we can compare the actions to each other's. And this function, we call it a heuristic in this paper. So you can see that your epsilon greedy just become applying a heuristic to the Q set and then using the argmax. So now this is a scalar, so now this is fixed. Well, many performance indicator exists from the multi-objective optimization literature, and actually they can be just taken out of the box and applied to this problem. For example, here we have the hypervolume indicator, which is quite common. So the hypervolume is defined by the volume between a pessimistic point, so for example zref in the graph here, and the solution point, so the points in your Q set. And you take the volume of that and it makes a scalar so that you can compare actually the moves. So for example here, going to the left only leads me to 1 move. However, going down leads me to 2 moves. So if I want to learn multiple policy, it is more interesting for me to go down. Okay, so now the exploitation is already tackled, so let's see for the exploration. So we are still in the training part, and yes, so actually 2 observations. First one is that there is no need for the agent at this moment to become greedy when training, because we don't have the true user utility yet. So we cannot say one strategy is better than the other. Second observation is that most of the existing work relies on sometimes decaying epsilon greedy to control the exploration of the agent. And it is actually understandable because this field is quite new, so we didn't have the time to explore exotic exploration strategy. Fortunately, what we try to do in this paper is actually to do that. So we try to propose new ways to do some exploration in those problems. So our idea is again here to transpose concepts coming from optimization to multi-objective reinforcement learning. And what we propose is to use meta-heuristics to control the exploratory part of the agent. So our scalarized epsilon greedy becomes actually entirely controlled by meta-heuristics that we will detail later. But first, let's take a step back and see the full picture, the full learning algorithm, so that everything is clear. So our agent is training for n episodes. Remember, it's offline learning. And so yeah, we restart the environment, and while we do not find the terminal state, we choose an action, and the action is chosen according to the exploration-exploitation dilemma. Once we perform the action, we receive the reward vector and the next observation, line 8. And using the Q sets, we apply the learning algorithm. Actually, the learning, we have multiple learning algorithms existing at the moment, so we can choose. And finally, we update the state. And finally, we return the Q sets. So the good part of this algorithm is that we can change the exploration, we can change the exploitation, and we can change the learning without the need to change any other one. So it really helps to, like in the research, to try new things. Let us see now, for example, the meta-heuristics that we propose. So the first one that we propose is called taboo. It is really common in optimization. The idea is to forbid recently made moves. So for example, if the submarine took a path, the episode after, it is forbidden to take the exact same path. So, and the main logic of the algorithm is that if there are one move or more which are allowed, you use the heuristic, so you use the exploitation to choose the best move. Otherwise, you choose a random move because everything is forbidden. So for example, in episode 1, we can see that the submarine is going to the treasure number 3, but in episode 2, now we see that the path to 3 is forbidden. So the submarine has to go to 1. And then in episode 3, the 2 possible paths are forbidden, so it chooses randomly, so in that case it chooses right, and then it goes to 5 because it's not forbidden. So it really helps to discover the various treasures. The second meta-heuristic that we propose to use is called repulsive pheromone, and the idea is to leave a smelly odor on the taken path, just like ants do. So yes, so and if those pheromones, they evaporate over time. So we use the score here to choose the best action. So for example, in first episode we go to 3, and it leaves a pheromone, but still the pheromones, they do not forbid strictly. You can still pass through. They just decay the value of making that move. So the submarine goes to 2 in episode 2, but then in episode 3, as you can see, 2 is really bad, so it goes to 5. Well, let's see our experiments. So we tried various exploration strategies on 2 environments. So the first one is the deep sea treasure that I presented. The second one is a new one that we introduced. It's called the mirror deep sea treasure, which is actually much harder than the deep sea treasure because the left part of the problem is a dead end. So it's not good to explore. And also the pathway between the 2 parts is really narrow. So for an agent that is currently exploring, it's really easy to fall into the treasure 1 or 2, for example, and to end the episode. So we are losing time to learn. The exploration strategies that we use is 2 state-of-the-art. So the epsilon greedy. Decaying epsilon greedy makes the agent becomes greedier at the end of the training. And constant epsilon greedy keeps a constant probability of choosing a random move. Meta-heuristics, so I presented the taboo-based and the pheromones-based, but there is also the count-based, which is really similar to the pheromones-based. If you want to have more details, you can always read the paper. And for the metrics, we used average hypervolume of the learned policies seen from the initial state. We average over 40 runs, do 95% confidence interval, and also statistical test as to ensure everything is statistically significant. Well, the results, so for the deep sea treasure, it's a no-brainer. The meta-heuristics are doing better for training than the current state-of-the-art epsilon greedy. Plus, we have statistical confidence of improvement. So for example, you can see that the pheromones and the count-based, they are learning the full front, so they are learning all of the strategies in less than 3,000 episodes. Taboo-based is not able to retrieve all of them. However, you can see that the epsilon greedies, so the decaying epsilon greedy becomes actually greedy. So as you can see, it doesn't learn much after 500 episodes, while the constant epsilon greedy still learns, but its confidence interval grows as well. The same kind of results apply to the mirror deep sea treasure, which confirms our claim. So here there's nothing to add. And yeah, so to wrap up, I presented multi-policy, multi-objective reinforcement learning. It's a technique which allows us to learn multiple optimal behaviors for our agent when we have multiple objectives to deal with. We present a new environment, the mirror deep sea treasure, and we see that our meta-heuristics-based exploration strategies are showing better results than the current state-of-the-art on the studied environments. And finally, our next steps will be to test these algorithms on actual robots and new benchmark to see how they behave. And I want to thank you for your attention, and if you have any question, you can feel free to shoot.